Okay, so let's talk about some of the things that affect solubility in the second half of this solutions video. So obviously the nature of the solute solvent, the type of IMFAs, the strength of the IMFAs, the attractions, and so on and so forth are going to help dictate it. So the whole idea of like dissolves like falls under this idea, like I said, the IMFAs. But there's a few other things as well. The amount of solvent that you actually have. How much water do I have dissolving it? Does it make sense that the more water I use, the more solute I can dissolve? Third idea, and this is pretty critical in many cases, is temperature. Liquids and solids typically increase in solubility as you increase the temperature. So the kinetic energy of motion increases. So you got collisions happening between the solute and the solvent. You're breaking those IMFAs apart, and so you're more easily able to dissolve solids and liquids if you raise the temperature. However, with gases, solubility is going to decrease with temperature because if you get those gas molecules moving faster and faster and faster, you're not going to be able to break you're going to break those IMFAs and even the solvent solute IMFAs, and so those gases are going to be able to escape into the atmosphere. So solubility increases typically with temperature in solids and liquids, but once you have a gas, then your solubility goes down because the gases are able to escape. Fourth factor is pressure, which obviously only is going to affect gases. It's not really going to affect liquids and solids. If you increase the pressure, you're going to be able to get more of the gas to dissolve because you're forcing it, you're compressing it together. So increasing the pressure will mean that the gas is able to dissolve more easily. This can be expressed through an equation called Henry's law. Henry's law shows you that the solubility of the gas is proportional to the partial pressure of a gas, and a constant is included there as well. And each constant is going to be different. So you change the solute, you change the solvent, you change the temperature, you change the K. So you need to have, you can't just solve for this, you need to have a list of K values, which means this equation is actually more practical when you take a look at conditions that are changing as opposed to just trying to figure out a baseline condition. So here is a very ugly stretched out curve of the solubility of potassium nitrate. Couple of things of interest to us in this curve. So please notice that you've got the solubility, the amount of solute that can dissolve, in this case in 100 milliliters or 100 grams of water. You always need to specify how much solvent you're using because solubility changes. You also need to specify what temperature you've got. And so we've got a few different things going on. This line actually represents the point of saturation. Okay, that was weird. The line represents the maximum amount of solute that you can have dissolved under these certain conditions. So if I have 100 grams of water at 100 degrees Celsius, I can get about 250 grams of KNO3 to dissolve. Okay, if at that temperature I have less than 250 grams of KNO3, that's what's referred to as an unsaturated solution because I could get more to go into the solution. I could get more to dissolve, so that's unsaturated. If we take a look at above the line, this really represents saturation points. So anything above the line, you have a saturated solution, and if you have excess solute, so if we go back to our line, if I try and add 300 grams of KNO3 into 100 grams of water at 100 degrees Celsius, I will wind up having extra solute sitting on the bottom of the beaker. It will not dissolve. Okay, that's typically what you're going to have. There are rare occasions when you can actually get something referred to as a supersaturated solution. It's like a magic trick. With any luck, when we get into class to discuss this video, I will be able to do a demo of a supersaturated solution for you. But basically, it's created by heating the solution up So if I put 300 grams, I'm going to heat it up to get it to dissolve and then let it cool very slowly and hope that when it hits the saturation line, it just doesn't start precipitating out and we start following the line. Hopefully it stays dissolved and just keeps moving back. So ideally, we've got more solute dissolved than what we really should. We're only supposed to have about 250, but if we can get all 300 of it to stay dissolved, that is a supersaturated solution. Again, those are very rare. They don't happen very often, but sodium acetate is one thing that does. We're going to hope that we can see that demo. All right. Solubilities of solids are going to vary, again, depending upon the IMFAs, depending upon the lattice energy, and so on and so forth. So here's just some examples. Most solubilities increase with temperature, as you can see, but they're not all linear. They increase very differently. There's no net pattern, so you can't predict the solubility of something without knowing a whole lot of information about that material. And occasionally you have a salt with a negative heat of solution so that it becomes less soluble as the temperature goes up. But that, again, not very often. Gases are exactly opposite. As you increase the temperature, the solubility actually decreases. So there you see the downward curves. And then finally, different ways of expressing concentration. You know, of course, that the most common way is with molarity. That's what we've always used. Moles of solute per liter of solution. But there's a lot of other ways of expressing concentration. Some of these you've probably heard, some of them maybe not. Mass percent or parts per hundred, how much solute in the solution times 100 gives you that mass percent. Parts per thousand, basically we're doing the same thing here, except instead of multiplying by 100 to give it to percent, we're multiplying it by 1,000 to put it in parts per thousand, parts per million, and parts per billion. Again, everything is essentially calculated the same way. You're just going to use parts per billion if you have really, really, really small quantity of solute. So the smaller the concentration, the higher you can go in parts per thousand, parts per million, parts per billion. Mole fraction we've seen in gases, the moles of solute in the total number of moles of solution. We saw that mole fraction when we were taking a look at partial pressures of gases in mixtures. So same idea, moles of the solute out of the total moles. And then molality is something that is a little bit different because notice that it's still moles of solute, but here we have kilograms of solvent. This is the only expression of concentration where you're not looking at the whole thing in the denominator, the whole solution, but you're only looking at the amount of water. And this is used when the temperature is going to vary because as temperature varies, excuse me, you can influence the solubility, but the total mass of the solution is not going to change, even though the volume might actually change. So we need to take a look at kilograms of solvent in that case. We don't use molality very often. I don't know of any, I don't even remember from grad school or undergrad if I used molality in any practical purposes, but it's out there. Percent concentration you can express in 3 different ways. Percent by mass, weight per volume, and then percent volume. So the units are just changing. Notice it's this amount of solute at the top, regardless of what expression of solute you have. And it's always solution on the bottom, again, regardless of what measurement of solution you're taking a look at. All right, so that gets us through the basics of solutions. Like I said, most of this you should have already known. We will talk about any questions that might arise from your reading as well as the video when we get back together in class.